Welcome to Spring LIB.
Okay, so we're doing chapter 29, problem number 3. So in this problem, we're talking about a way to measure magnetic field strength, and one to do that is to use search coils. So a search coil is just a coil here with N turns. Each, looking at it from the top, you see these circles, each with a cross-sectional area of A. Okay, so how these work is the coil is either quickly rotated or, before that, this is also held near a magnetic field perpendicular to this. So here is the magnetic field, the B field, and then to measure the magnetic field strength, you can either quickly turn the coil a quarter turn about a diameter or quickly pull it out of the field. So we want to derive, part A wants us to derive the equation that relates the total charge that's going to flow through this current to the magnetic field strength B. We want to figure out what kind of relationship is here. Okay, so to do this, they give us some information. So they say that N turns in the coil, each cross-section area is A. So it also says the flux initially, so magnetic flux at time equals 0 is at the maximum. So I'll just call this flux max, and then it is decreased over a time delta t, so t equals delta t to 0. Okay, so we start with the maximum flux and then we move it to 0 as we pull the charge or the coil outside of the magnetic field. So the coil also is given resistance R, and the total charge they give us is given as the average current over the time it has flux, delta t. Okay, so we need to relate this equation. So first we got to figure out how we're going to figure out what this average current is. To know this, we got to figure out how a magnetic field can induce a current on this, and that is called by Faraday's law. So using Faraday's law, we know that the average EMF is given as the N turns in the coil times the change in magnetic flux over delta t. Okay, so now we can write this out as N. Since we know that the change in delta flux is the final minus the initial, we know that, and it's an absolute value, we're just looking for the magnitude, so that's just given as phi max, or our maximum flux. So we take this, so call this phi max all over delta t. Awesome. So they also tell us that the orientation here is exactly perpendicular to the current. So we know that flux is given as B times the cross-sectional area, since it's exactly perpendicular. So this phi max is B times A, so we can relate our average EMF as N times B A over delta T. Perfect. So now we know the average EMF induced, and then to get the average current from that EMF, we just use Ohm's law. So Ohm's law says the current is given as the average EMF or voltage over the resistance. And the resistance of our coil is just R. So we can just plug our equation in here and we're given NBA over R delta T. Okay, and so this is our average current. And now we just plug this back into our original equation given here, and we know Q is NBA over R. The delta T's cancel out. Awesome. So let's move on to B. So what B asks us is, in a credit card reader, the magnetic strip is on the back of a credit card is rapidly swiped past a coil within the reader. Explain using the same ideas that underlie the operation of a search coil how the magnetic how the reader can decode the information stored in the pattern of the magnetization on the strip. Okay, so if our card reader or card here is swiped real fast, these are given out a B field, right? At each point, we have some pattern of B fields here, of magnetic fields on the card. And this pattern of B fields is what gives you the signature of this particular card. So if you can use the search coil to read Q as a function of time as these B fields getting swept through, this only depends on these coil parameters in A and R, and the B field is also measured as a function of time. So if you know a particular pattern of a B field as a function of time, the search coil is going to let you read out the charge as a function of time, so you can just scale it by these coil parameters, and you can read exactly this information decoded in the magnetic fields of the card. So that's how these magnetic strip card readers work. Awesome. So now let's get a new page here. Let's move on to C. So what C asks us is it necessary that the card be swiped through the reader at exactly the right speed? Why or why not? Okay, well, if we go back to what our equation was, it was just given as this, right? So if we're reading the charge, our search coil is reading just the charge. It doesn't depend on how fast these B fields get changed. So delta t, as it canceled out, means that the speed doesn't matter. So that's perfect, because obviously no one is going to swipe their card at exactly the same speed. So since the delta t's cancel, then we can swipe our card however fast we want. Awesome.